So we will start with this lecture, talk about integration. So the point will be to consider. So we have a space, a sigma algebra of subsets of this space, a measure which is defined on this sigma algebra. And now we will have functions which are defined on omega and take values in R union minus infinity plus infinity. And we would like to define the integral of f, which I will represent by I of f. And we will require some properties of this integral. Of course, we will want the integral to be linear. So if we multiply our function by a constant alpha, and if we sum, so we would like the integral of this new function to be alpha times I of f plus I of g. So it's a reasonable property. We would like also, say, I of f to be defined for the largest possible class of functions, and we will like some continuity properties of this functional. So typically say that if we have a sequence of functions fn which increase to some function f, say that the fn are all non-negative, then it will be reasonable to expect that the integral of fn will converge to the integral of f. One property which is also quite natural is that the integral of a non-negative function to be non-negative, so that we expect this functional to be such that if we have a function which takes only non-negative values, we expect the integral also to be non-negative. So these are, say, some essential properties of this object I, which we will define in these next lectures. And before we do that, let me compare a bit what this integral, the idea of defining this integral, with the idea of the Riemann integral. So let's say that, so it's very informal what I will say now. I'm just telling you this to introduce some concepts which will be important. So let's say that we have here the space omega. Let's say that here it's R. So we have a function which is defined on omega and which takes values on R. I just draw its graph. So how would you define the Riemann integral? Well, let's say that omega is equal to R, so you'll divide R in small intervals. In one of these intervals, you consider the value of the function at one point. If the oscillation of the function in this interval is small, you'll say, well, that the integral of f, well, it will be close to, let's say that we have here an interval ij. We will take, well, the length of the interval ij times the value of the function at one of these points. So let's say that we have xj, which is a point in ij. And we will say, well, that the integral of f should be close to the sum of fxj times, let me represent by this symbol, the length of the interval ij. So this is what, there is a sum over j, which is maybe you want to define this integral in an interval ab, so that this sum will be finite, and well, we expect that as the length of these intervals vanish, that this sum will approximate the integral of f. So this is the idea behind the definition of the Riemann integral, right? So now we will adopt a completely different point of view. Here again it's the set omega, here is the set r. So instead of dividing omega in small intervals, we will divide the y-axis in small intervals. So we divide the y-axis, which is r, in small intervals. Here again is your function, the graph of the function f. And what you will do, it's you'll consider all points. All points whose image is in this interval. So we'll take the inverse image of this interval, which in my example is, say, this set here, let's say A. And so the idea, so I'm taking this interval, let me call it jk. Let me take a point xk, or let me call it yk, not to mix with xj defined previously. So let me take yk in this interval gk. And the idea will be to define the integral of the function f as something which should be close to, well, in the function f, take values in this interval gk when it belongs to A. So, and let me call that ak. So ak is let me call this function f. So we take the inverse image of the interval jk, and I'm calling that ak. So it will be reasonable to define the integral of f as something which should be close to, well, here jk, I'm taking a point yk, so f takes the value yk in this set ak. So let me assume that in this set omega there is a sigma algebra and there is a measure which I'm representing by mu. So I'm here taking mu of ak, which is equal to mu of the inverse image by f of the interval gk. Right, so we expect, well, we would like the integral of f to be close to the sum in over k of yk mu, the measure of the set which is the inverse of by f of the interval gk. So, so we are changing the perspective. Instead of dividing the set omega in small intervals, we are dividing now the set R in small intervals, and we are taking the inverse image of these small intervals to define the integral. Right, so that would be also a natural way in which to approximate what we understand as the integral of a function f. However, and here's my point, mu, so there is a set omega, there is a sigma algebra f, and there is a measure mu, and mu is defined on the sigma algebra f. So my point is that in order for this measure to make sense, we need this set to belong to the sigma algebra f, right? Because mu is defined only on the sigma algebra f. So, in order to make sense of this quantity, we need the inverse image of an interval to belong to the sigma algebra f. So it makes sense to introduce a definition, which I'll make it formal in a second. So we have a function from omega to, let's say for the moment, r. And we are taking here an interval in r, and we are taking its pre-image, and we are requiring the pre-image to belong to the sigma algebra F. So it will make it's natural to define a class of functions for which, let's say, f minus 1 of a belongs to f for any a in the Borel sigma algebra of R, right? Because, well, here we are taking intervals, so requiring that for all intervals, we will see that it's the same, it's equivalent to require that for all intervals or for all elements of the Borel sigma algebra. So it makes sense to introduce this class of functions, the functions for which the inverse image of any element of the Borel sigma algebra belongs to sigma algebra F, and this will be called the measurable functions. So it's in order to be able to define the integral in this sense that we will introduce this notion of measurability, which will be the topic of today's lecture. Let's start, therefore, our lecture of today by defining measurable functions. So I will from now on fix a set omega, a sigma algebra F, and a measure mu, which is defined in the sigma algebra F. And so I consider a function f, which is defined on omega and take values in r. And in fact, I will allow f to take values minus and plus infinity. And I will call this extended line by r bar. And so we have a sigma algebra here, which is the Borel sigma algebra, which is the sigma algebra generated by the open sets. So I will represent by B bar all sets which can be written as a set. These are defined by all sets which can be written as A union B, where A it's an element of the Borel sigma algebra, and B is a subset of minus infinity plus infinity. Right. So I leave to you to check that B bar it's a sigma algebra. And I will call it the extended Borel sigma algebra. And therefore, I will say that a function defined on a measure space. So measure space will be a triple in which we have a set, sigma algebra of subsets of this set, and a measure defined on this sigma algebra. So given this measurable space, I would say that a function taking values in the set R extended is measurable well if the inverse image of any set A in B bar belongs to F. So and we have seen why we define this concept of measurability, because it will be important in order to define the integral of the function f. Right? So we'll say that some function f is measurable if for all sets A in B bar, the inverse image by f of A belongs to the sigma algebra F. Okay? If I want to, it might be possible that at some point we have in some set omega many sigma algebra defined. So we could have now sigma algebra F, another one G. So if I want to make precise that it's measurable with respect to this sigma algebra F, I would say that it's F measurable, right? Observe that this definition is, well, if we have two sigma algebras F and G, a function may be measurable with respect to F and not measurable with respect to G. It's clear, well, it's an observation which is obvious. If F, it's contained in G. If a function is F measurable, then it's of course G measurable. So if I want to make precise to which sigma algebra I'm referring, I will say that the function is F measurable. So this is an important definition, and of course it might look that it will be difficult to check if a function is measurable or not, because we'll need to verify if for any set A in the sigma algebra B bar, F, the inverse image of A belongs to F. But I will now state a lemma which asserts that it's not, you don't need to check this relation for all sets, but just for a subfamily of sets. And this is, we will rely on this lemma whenever we want to prove that some function is measurable. So let me state this function, this lemma. So let me state the lemma. So we have in this lemma a measure space and a function which is defined in omega and take values in R bar. And I will say that F is measurable if and only if one of the following conditions holds. So the first condition is that the inverse image of the sets minus infinity x belongs to F for any x in R. Or B, that the inverse image of minus infinity open at x belongs to F for any x. Or C, that the inverse image of x infinity belongs to F for any x in R. Or D, the inverse image of x infinity belongs to F for any x in R. So in order to show that a function is measurable, we need only to check that the inverse image of, say, this type of set belongs to F. So remember, this will be all the points omega in omega such that F of omega is less or equal than x. So we need to show that for any x in R, this set belongs to the sigma algebra F in order to prove that a function F defined in omega is measurable. Right? So what I will do, I will prove A, and what I claim is that the same argument applies to any of these statements. You can also prove that they are all equivalent. So I leave it to you to complete the details. I will just prove that a function is measurable if and only if A holds for any x. The proof of this assertion is very simple, but the method, the technique that we will use is very important, and it will be used many, many times in these lectures. So I will present it in with details. So there is one direction which is very simple. I claim that if f is measurable, then f minus 1 of minus infinity x belongs to f for any x in R. Okay, well, this is clear because, well, the set minus infinity x belongs to the sigma algebra of the Borel. Therefore, it belongs to the extended sigma algebra B bar. And therefore, by definition, its inverse image belongs to f because f is measurable. Okay, so this direction, it's elementary. So it's the reversed, the converse statement which requires an argument. Right? So now we know that the inverse image of all these sets is measurable, and we want to show that in fact the inverse image of any set in the extended Borel sigma algebra belongs to f. And the problem is that we don't have a description of the sets which belong to the extended Borel sigma algebra. So we cannot just take a set, take its inverse image by f, and try to prove that this inverse image belongs to f. We have to proceed in a different way. And here is the idea. Well, we'll define a class of sets, which I'm calling C. C will be all sets A in, say, B bar, such that the inverse image of A belongs to F. So I'm introducing a class of sets denoted by C. And what I will prove is that this class of sets has two properties. The first one is that it forms a sigma algebra, so that C is a sigma algebra. Right? And that, so if I know that C is a sigma algebra, I know that C, and if I prove that C contains a set, let's say, let me call it G, then from these two properties, knowing that C is a sigma algebra and C contains a sigma algebra G, I will conclude that C contains the sigma algebra generated by G. And if this sigma algebra generated by G it's larger than the sigma algebra, the extended Borel sigma algebra, I would have I would have proved that C in fact contains all sets in the extended Borel sigma algebra, and therefore I would have proved that F is measurable because this is exactly the property defining C. Right? So the strategy of this proof is to show that C is a sigma algebra and that C contains a family of sets which generate the extended Borel sigma algebra. So here it's the sets, the family G, it's clear. The family G will be the family of sets minus infinity x, such that x belongs to R. So let me represent all intervals minus infinity x with x in R as G. By assumption, this class of sets G, it's contained in C, because the inverse image by F of these sets are in are in F, and they all belong to the extended Borel sigma algebra. So if I represent by G this class of sets, it's clear that this class of sets is contained in C, and we also know that these sets generate the extended Borel sigma algebra. So G has the two properties we wanted. First, it is contained in C, and then it generates the extended Borel sigma algebra. So what it remains now to do is to show that C is a sigma algebra. And this is what I will do. So we want to prove that C is a sigma algebra. To prove that C is a sigma algebra, we need to check three properties. The first one is that omega that R extended belongs to C. Well, R extended, it's certainly an element of the extended Borel sigma algebra, so this is one fact. And now we have to show that if we take the inverse image of R extended, it belongs to the sigma algebra F, but this is the set of all points omega in omega, such that F of omega belongs to the set R extended, and this is just equal to omega, which belongs to the sigma algebra F, and therefore it's indeed true that R bar belongs to C. So now the second property of C is that it's closed by complement, so I'm assuming that some set A belongs to C, and I want to show that A complement belongs to C. So let's start with a set A in C. If A belongs to C, this means that the inverse image of A belongs to the sigma algebra F. And now to prove that A complement belongs to C, well, if A belongs to C, A belongs to the extended Borel sigma algebra. Since it's a sigma algebra, A complement also belongs to the extended Borel sigma algebra. Now let's prove that if I take the inverse image of A complement, it belongs to C. Well, but I leave to you to check that this is just the inverse image of A complement. And well, since the inverse image of A by F belongs to the sigma algebra F, its complement also belongs to F, which proves that A complement belongs to C. So we have just seen that C is closed by complement. Now let's prove that C is closed by countable unions. So take AJ, a countable family in C, and we want to show that the union of AJ belongs to C. Well, this is also easy. Well, AJ belongs to C means that AJ, among other things, means that AJ belongs to the extended Borel sigma algebra. Since it's a sigma algebra, the union of AJ belongs to the extended Borel sigma algebra. So what remains to be shown is that the inverse image of the union is in F. But again, I claim that if you take union of sets and you take the inverse image, this is equal to the union of the inverse images. Well, since AJ belongs to C, this means that the inverse image of AJ belongs to the sigma algebra F. And since F is a sigma algebra, the countable union of elements in the sigma algebra also belongs to the sigma algebra F. And this proves that the union of AJ is indeed in the class C, which proves that C is a sigma algebra. So I will insist on this, on the technique we used in this proof. So we wanted to show that starting from a family, the class of sets which had certain property, which I called C. So we wanted to show that some class of sets, which is here denoted by C, is sigma algebra which contains the extended Borel sigma algebra. So we proceed in two steps. We first show that this class is a sigma algebra, and then we prove that this class contains a family of sets which generates the Borel extended sigma algebra. So this technique will be used systematically in the next lectures. We want to show that some property, the sets which share some property contains a sigma algebra. We will prove that the class of sets which have this property forms a sigma algebra and contains a generating class of sets. We sometimes, instead of using this property, we use the monotone class theorem, which tells you that the monotone class generated by an algebra coincides with the sigma algebra generated by this algebra. So we'll show that this class is a monotone class and it contains the algebra and therefore contains the sigma algebra. So this is also a second way in order to prove that some property is satisfied by a certain sigma algebra. So the proof, as you've seen, is very elementary. It's just that the approach, the idea which is very important, and I want you to remember it. So let me give you an example of measurable functions. These will be called the simple functions. So assume that you have a finite family EJ of subsets. So all these EJ are subsets of omega. So again, remember that we are working with a set omega, a sigma algebra, and a certain measure mu. Assume that these EJs are all subsets of omega which belong to the sigma algebra F, and that they are disjoint 2 by 2. So the intersection is empty if J is different from K. So I'll define a function F which will be equal to Cj. So Cj will be a real number in the set Ej. So as I said, Cj here are real numbers. They might be equal. I'm not imposing them to be different. And I'm representing by this symbol 1ej, the indicator of the set Ej. So this is a function from omega to r, extended, which associates to a point omega the value 1ej omega, which is either 1 if omega belongs to Ej, or 0 if omega does not belong to Ej. Right? So this is the indicator of the set Ej. So I'm taking here, I'm defining a function f, which on the set Ej takes the value Cj. And Ej are all sets in the sigma algebra which are disjoint 2 by 2. And let me observe that I'm not requiring EJ to form a partition, but I don't lose any generality requiring that the union of EJ it's equal to omega, because if this is not the case, I can always introduce a set E0, which would be omega minus the union of EK, k from 1 to n. Clearly, E0 is an element of the sigma algebra F, and E0 it's, has no intersection with respect to all the other sets. And here I can just assume C0 to be equal to 0 and rewrite this expression as a sum from 0 to n. So there is no loss of generality requiring that in fact this class of sets EJ forms a partition of the set omega. And if I can write a function f in such a way, I will say that f it's a simple function. So this is a definition. I'll say that a function f from omega to r is a simple function if there exists a partition of the set omega by elements in the sigma algebra, and if there exists a sequence, finite sequence of real numbers Cj, such that f can be written as the finite sum of Cj times the indicator of the set Ej. So these will be the simple functions, and what I claim is that the simple functions are measurable. Well, why is that so? Well, because if you take the inverse image of any set A, well, this, so take A a subset of R, if you want, or more, take A as an element of the extended Borel sigma algebra. What I claim is that if you take the inverse image of this set A, this is always equal to a union of Ek, but I'm not taking all Eks, I'm taking a sum over all indices K, such that Ck belongs to A. So what I claim is that the inverse image of a set A is a union of the sets Ek, which Ks I'm taking in this union, all the Ks such for which Ck belongs to A. And of course, whatever our choice here, this is an element of the sigma algebra F, and therefore for any, we just proved that for any subset A in the extended Borel sigma algebra, the inverse image by F by this simple function of A is in the sigma algebra, and therefore F is measurable. So we have here examples of measurable functions. So let me now consider a simple function f. So f defined in omega and take values in R. And let me represent f by a sum of indicators Ej. So here, remember, I'm assuming that Ej it's an element of the sigma algebra F, and that the family E1, Ej, En forms a partition of the set omega. So what would be a natural definition of the integral of f, keeping in mind the informal idea I presented at the beginning of this lecture. So what's happening here is that this function take only the values c1, c2, let's say that they are all, that it could be negative, but let me represent them by non-negative numbers. So Cn, and remember that I'm not requiring these values Cj to be different, they can be equal, so you can have more than one index j for which taking the same value. So if I take the inverse image of Cn, what I find here, it's a set En. And if I take the inverse image of C2, I get another set here, which is E2, and so on. So it would be natural to define the integral of f, of this simple function f, as, well, I'm taking the value Cj, I consider the inverse image of Cj. The inverse image of Cj, it's Ej. It can be more sets because maybe Cj is equal to Ck. But then I'll multiply that by the measure of Uj, and then I will sum over all its values, and this would be a reasonable definition of the integral of the simple function f. However, we have to be careful here, is that maybe Ej has measure plus infinity. So if I have here a positive value multiplying plus infinity and then a negative value multiplying plus infinity, I have an expression which is not well defined. So let's assume that all Cj's are non-negative, then this makes sense. It can be equal to plus infinity if one of these sets has measure equal to plus infinity, but this sum makes sense. Of course, I have also to show that this integral is well defined, because same simple function may have two different representations, and I have to check that in the case in which I have another representation of the same function, same simple function f, the right-hand side it's equal independent of the representation. So suppose that I have this function f, which is also written as a sum from 1 to n of different values dk and the indicator of a set fk. So I'm assuming that the same function, simple function f, has two different representations, one as the sum of Cj times the indicator of Ej, and the other one as dk, the sum of dk's times the indicator functions of fk. I'm assuming here that fk are all sets in the sigma algebra F, and that they form a partition of the set omega, though I'm not writing these assumptions. Well, my observation is the following. Well, if Ej, so take a set Ej, take a set Fk, Ej intersection Fk might be empty or might be not be empty. So assume that it's not empty. Well, if it's not empty, if I take a set omega, a point omega, which belongs to the intersection, on the one hand, f omega, so maybe let me denote that by g naught, k naught. On the one hand, by the first definition, since omega belongs to Ej naught, the indicator of Ej at omega vanish because Ej forms a partition for all j different from j naught. And at j naught, this is equal to 1. So f of omega, from this formula, it's equal to c j naught, right? Because the indicator of Ej naught at omega it's 1, while for all the other ones it's 0. For the same reasons, considering the second representation of f, if I, since omega belongs to fk0 and fk forms a partition of the set omega, the indicator of fk at omega will be equal to 0 for all k's, but for k equal to k0, k0. So the sum will be reduced to k equal to k0. In this case, this indicator is 1, and here we get dk0. So f of omega will be equal to dk0. So this means that whenever the intersection of these two sets is not empty, then Cj0 it's equal to dk0, right? So let me write the conclusion. In this case, we have that Cj0 should be equal to dk0. So let me erase the argument and just keep the conclusion. And now what I would like to show is that the integral of f by using the first representation coincides with the integral of f by using the second representation. This means that I need to show that the sum from 1 to n of Cj mu of Ej, it's equal to the sum from k from 1 up to m of dk mu fk. Well, but since fk forms a partition of omega, mu of Ej, which is equal to mu of Ej intersection omega, but omega is the union of the fk So let me distribute the intersection through the union. So this is equal to mu of the sum from 1 to m of Ej intersection fk. And since fk forms a partition, all these sets are disjoint. So by additivity of mu, this is equal to the sum from 1 to m of mu Ej intersection fk. Right? So I proved that mu Ej it's equal to the sum in k of mu of Ej intersection fk. So I will just rewrite this conclusion here. So this is a sum from 1 to m, a sum of k from 1 to m, Cj mu Ej intersection fk. Right? Well, but now either Ej intersection fk is empty. If Ej intersection fk is empty, the measure of the empty set is 0. Or Ej intersection fk is not empty. In this case, if it's not empty, this means that Cj it's equal to dk. So I can replace here Cj by dk. So the conclusion is that I can always replace Cj by dk. Why? Well, because if Ej intersection fk is empty, this measure is 0, and therefore I have 0 times Cj, which is equal to 0 times dk. On the other hand, if Ej intersection fk is not empty, then Cj is equal to dk, and therefore I can replace also Cj by dk. So this means that I can always, in all cases, I can replace Cj by dk and I can now just repeat the argument backward, which means that I will sum over j, and use the fact that Ej forms a partition of omega to claim that this is equal to, these are finite sums, these are positive numbers, so I can always change the order of summation and sum first in j, and while summing in j, using the fact that Ej forms a partition, we get that this sum is equal to dk times mu of fk, which proves that the sum of Cj mu Ej is equal to the sum in k of dk mu fk, and therefore that the integral of a simple function is well defined by this formula because it does not depend on the representation of the simple function. So this will be our definition of a non-negative simple function, right? Remember that we assumed Cj to be non-negative just to make sure that this sum is well defined. So if I have a function f defined in omega which is simple and takes non-negative values, I will define I of f, the integral of f, by this formula. Well, we just defined the integral of a non-negative simple function. So let me just indicate how we will proceed. We will first show that if you have a function which is non-negative, might take a value equal to plus infinity, and which is measurable, then I will always be able to find a sequence fn of simple functions. So the fn are simple functions which are non-negative and which increase to f. So we'll first prove that. So if you take a non-negative measurable function, we can always find a sequence, a monotone sequence of non-negative simple functions which increase to f. Then, well, we want to extend the definition of the integral of f to non-negative measurable functions. What we will do? Well, we will consider such a sequence and we will call I of f as the limit of such a sequence. Of course, here again, we will have to show that I of f is well defined, right? Because it's clear that you can find more than one sequence of simple functions which converge monotonically to f. We have to show that this definition does not depend on the sequence chosen. Once we prove that, then you consider a measurable function now. So now, which might take negative values and positive values. First, I will define the positive part. So let's recall that I'm assuming this function to be measurable. So let's define by f plus the positive part of f. So that will be the maximum between f and 0. And in the same way, I will define the negative part, which will be represented by f minus, which is the minimum of minus f and 0. I'm sorry, the maximum between minus f and 0, which is also non-negative. So these two functions are, we will show, measurable. They are measurable. We'll have to show that. Well, it's clear that f can be written as f plus minus f minus. Observe that they can't be both equal to plus infinity, because if f plus is equal to plus infinity, then f minus is 0, and conversely. So we have, f plus and f minus are non-negative and are measurable. So I of f plus is well defined. I of f minus, it's also well defined by step 2. So if both are finite, or at least if one of them is finite, I can define I of f as the difference of these two integrals, and this will be the definition of the integral of a function f. So we will say that this function f, which is measurable, it's integrable if both integrals of the positive part and the negative part are finite, and we'll define it, the integral of f, as this difference. But it may happen that one of them it's plus infinity and the other one it's finite, in which case we can also define the integral of f by this formula. So that will be the steps that we will follow up to the definition of the integral of f. So observe that in this sequence of steps, we need to show that if we have a function which is measurable and we change it in some algebraic way, we obtain a measurable function. So in these next few minutes, I will show that if you start with a measurable function and you perform some algebraic transformation of this function, we still obtain measurable functions which are necessary results in order to complete the definition of the integral of a function. Let me also remark, before we go through these measurability questions, let me just remark that at this point we can define the integral of some functions which are not, whose Riemann integral is not well defined. So let's say that we take omega to be the interval 0, 1. Let's consider in 0, 1 the Borel sigma algebra in 0, 1. So the sigma algebra obtained by the open set of this interval. Let's consider the, let me represent by lambda the Lebesgue measure. So the measure on the Borel sigma algebra which extends the concept of length. So working with these sets, let's take E to be, let's say, the rationals intersection omega. And so now let's take the function f, which is the indicator of the complement of E in omega, right? So this is a simple function. So the integral of f by our previous definition, as it's a simple function, is just the measure of, which I'm representing by lambda, of E complement. Well, and you can show that the measure of the rational points, the Lebesgue measure of the rational points is 0. So the measure of the complement, it's the measure of the whole set, but the measure of the whole set is just 1. Right. So this function, which is measurable because it's simple, has a well-defined integral which is 1, but it doesn't have a Riemann integral because, well, the oscillation of this function, it's also always equal to 1 whatever interval you take. Therefore, you're not allowed to define its Riemann integral. So you see that in the way we defined the integral allows you already at this point to define integrals of functions whose Riemann integrals are not well defined.